welcome to another class on EE211. In today's class, we shall start the topics of the operation amplifier. Operation amplifiers are integrated circuits that are used to perform various mathematical functions such as summing, integration, differentiation, comparison, and wave shaping. The concept of operation amplifier is an advanced topic. However, in linear circuit analysis course, the concept of having the topics of operation amplifier is to identify and test the procedures to find out the output voltage using the Kirchhoff's current law and the node voltage method. There are few assumptions that we will see later on. So let us start with the topic of the operation amplifier. Operation amplifier is actually an integrated circuit. So let me write this. This is an integrated circuit. Integrated circuit is actually a chip that contains a lot of transistors that are connected in various configurations inside. Being a sophomore student and a very having the first course on electrical engineering, it is not our task to understand, to analyze the circuitry inside and how the internal transistor actually work. The procedure here shall adopt the very few assumptions that are widely used to identify and to analyze the output of an operation amplifier, and we shall use the basic techniques that we have learned so far to identify the output parameters and the region of operation for an operation amplifier. So it is actually an integrated circuit which comes in various versions, the most famous one being as the 741 operation amplifier. 741 operation amplifier is the most commonly used operation amplifier. It is an 8-pin IC. So let me draw down the dual inline package version of the 741. So we have a small groove here. In the data sheets, each of the pin has its own individual functions, right? So we need to first identify the pin configuration or the pin number. So we have a groove here, and right beside the groove is pin number 1. Then we have, as we come down, we have pin number 2, pin number 3, pin number 4, and going on with the same direction we have 5, pin number 6, pin number 7, and pin number 8. From these 8 pins, we perform all the functions that are required to perform any mathematical function. Here we have pin number 2 and 3 are the inputs where we shall apply the input signal, and we have pin number 6, we have the output here, right? This pin number 5 and pin number 1 are actually the offset nulls that are used to compensate the gradations in a circuit, and they are of no interest for this particular course. So but however, I will write this is an offset null. This is also an offset null. So we have, this is pin number 4 and pin number 7. These are the biasing supplies, because the all the functions that are used, that are performed by an operation amplifier, require some biasing supply. So we first need to power a circuit up. So after we power up the particular IC, only then we will be able to perform the circuit operations. So we have pin number 4 and pin number 7 here, where pin number 4 is the minus VCC and pin number 7 is the plus VCC. This pin number 8, it is actually not connected inside. It is only available because to avoid and to maintain the symmetry in this particular IC. So this has no internal connection, and I will write it as not connected. Remember that there are two inputs available. One of the input is known as an inverting input, and that is pin number 2. So we have negative input here, and we have a positive input at the pin number 3. Now, like every element that we have studied so far, operation amplifier has a symbol that is used in all the diagrams and all the circuits that we are going to study. Usually in some older books you might see symbols like this one as well, where we have this one positive, this negative, and here we have the output available. Most of the times in numericals you might not see these two pins which represents the biasing supply, plus VCC and the minus VCC. However, if they are not available in a given circuit, either they are stated in the numerical statement, or they are left on the choice of the user or the on the instinct of a student. So we have this positive and this negative. However, the textbook that we are following, most of the modern textbooks, they use this modern symbol here, which is actually quite similar with that of a play button. So we have this plus, we have this minus. All the voltages are measured with respect to the ground terminal. So we have this terminal grounded. This is VCC, or we call this one as a minus VCC. Then we have a plus VCC available here as well. So let me draw down this as well. So we have this is plus and this is minus, and this is the output. We have the positive input, we call it the VP, where this is the VP with this sign positive, and we have with respect to the ground terminal. Also, the voltage at the inverting input is known as the VN, right? And it also has a plus sign here with respect to the ground symbol. It is measured. Further to this, the current constraints are as follows: that we shall assume that all the currents move into the uh, operation amplifier. As we move forward, let us, for an operational amplifier, like its name implies, it is actually an amplifier. An amplifier is actually an electrical device or an electronic device which amplifies a given signal. Notice that any amplifier signal that is used to amplify an input signal or to reconstruct a signal and thereafter having an amplitude much more than the input signal, it requires it is only accomplished with the help of the biasing supplies. So we have two biasing supplies available here, which are the plus VCC and the minus VCC. Notice that the plus VCC and the minus VCC both are used to amplify the signals on the positive half side and on the negative half side. However, there is a limit of an operation amplifier. It is not possible to provide a 1 volt input and thereafter we get an output which is greater than the voltage of these biasing supplies. So based on this, we define the regions of operation of an operation amplifier. An operation amplifier has the following regions of operation, right? So we have, for instance, if we have, this is the differential voltage applied at the input, Vp minus Vn, and if this is the V naught available here, then we have this type of characteristics for an operation amplifier. Notice that this particular point is the plus VCC and this particular point is the minus VCC. So you see, all the amplification can only be processed, can only be done, can only be accomplished if the operation amplifier is operating in this linear region. If the gain of the amplifier is set too high, that it tends to cross the biasing supply voltage levels, plus VCC or the minus VCC, it is simply not possible for the operation amplifier to amplify the circuit, to amplify the given signal. So what happens is, if we increase the gain such that the theoretical output tends to go beyond the value of this plus VCC and the minus VCC, then the operation amplifier becomes saturated, and it only gives us these particular voltage level, which means that beyond these particular two points, the amplification is not possible. So henceforward, we can write the characteristic equation as that the minus VCC A times Vp minus V of n should be less than into plus VCC. Now this particular is of our interest. This output is amplified only in this particular region, and therefore this particular point is of much interest for us. So if we see the practical operation amplifiers available in market, most of the operation amplifiers have a nominal biasing supply voltages up to 20 volts. So let us say if we have a biasing supply voltage for a given operation amplifier, let us say that the biasing voltage is equal to plus minus 20 volt, right? So let us assume that we cannot have an output greater than this 20 volt, which means that the output can at maximum be able to go up to 20 volt. Next, there is always an open loop gain associated with in the data sheet, which is usually specified. And remember that operation amplifier tremendous amplification ratios A. So let us consider that the amplification ratio A is equal to, or the gain, open loop gain, let us say this is an open loop gain of a typical amplifier of op amp is, let us say it is equal to 10,000, or that is equal to 10 raised to the power 4. Now if we move back to this particular equation, this one, this is of our interest. So we do know that the output can be at a maximum value equal to 20 volt. Based on this particular assumption, we can write that if this V naught is equal to A times Vp minus Vn, and we know that V naught is equal to 20 volt and A is 10 raised to the power 4. So Vp minus V of n, we get a value difference that is equal to 2 millivolt. Notice that this 2 millivolt is a negligible quantity compared to the maximum output which is available, which is 20 volt. So henceforward we can say that Vp is approximately equal to Vn, and this particular concept is known as the virtual short concept. And virtual short concept is a very important concept in operational amplifier circuit analysis. Virtual short states that if we have an operation amplifier, for instance we have this operation amplifier here, and we know, for instance we have some circuitry across this particular point, and we have something available here as well. So we can say that if we do know what is the voltage here, which is Vn, then we do know what is the value Vp here. So either one of the 2 points, if we calculate the voltage at one of these two terminals, then it is obvious that the second terminal will also have the same voltage there. This is the first and the most important constraint in the operation amplifier. Another important constraint in an operation amplifier deals with the behavior of an ideal operation amplifier. An ideal operation amplifier has two important properties. Let me write them as well. An ideal op amp has an infinite input impedance. That is, we have R in equals to infinity. This means that this operation amplifier, the current going into this operation amplifier through this positive terminal or through this negative terminal, Ip is equal to In, that is equal to 0. So henceforward we can say that there is no current which enters the operation amplifier from the input terminals, which is the which are the pin number 2 and pin number 3, or the inverting and the non-inverting inputs. So we have Ip is equal to In, that is equal to 0. Moreover, we have output resistance equal to 0. So we have R out equal to 0. This means that based on these two constraints, we never know what is the current from the output terminal. And this is because of the fact that if you want to find out what is the output current, you first have to identify the currents in all the branches connected to with the output, and thereafter, after applying the Kirchhoff's current law, you can only establish what is the current flowing from the output of an operation amplifier. So therefore, as an important point to note, never try to solve an operation amplifier starting from the output node. We always try to start the operation amplifier analysis moving on from the input side. Of course, there are several scenarios that can be built up using the numericals, and there are different things that can be brought in while solving a given circuit. However, as a general step to follow, the analysis of operational amplifier begins from the input side, or the input terminals Vp and the Vn. Now that we have studied that an operation amplifier actually follows this particular region of operation, and this means that one should know when an operation amplifier is actually operating in a linear region, and when it is not operating in a linear region. To understand this further, we need to identify and we need to analyze it mathematically using the circuit analysis technique and these two important parameters that we have studied, these virtual short concept and the constraints of the input currents. After applying these two on an operation amplifier circuit, we are able to tell or whether an operation amplifier is working in a linear region or not. So for example, let me draw a given circuit. So we have an operation amplifier. So we have this equals to plus 10 volt, and we have this minus VCC equal to minus 10 volt, and we have VA connected with this particular point. Let us say this is 25 kilo ohm resistance, and this particular resistance is equal to 100 kilo ohm. That is, this is our V naught, and we have V. This is the negative input, this is the plus input, this is VB, and that is grounded. Assume that, let us have some values for this VA and VB. Let us say that VA is equal to 1 volt and VB is equal to 0 volt. Now, to start with the analysis of this particular circuit, we first need to identify if this particular operation amplifier is actually operating in a linear region or not. To do this, we shall first assign some values. So let us say this is Vn and this is Vp, right? Also, we say that this is In, which is the current flowing into the input terminal, and this is Ip. Now, from this particular point, we do know a few things from this particular circuit. The first thing is that In is equal to Ip is equal to 0, because input impedance is infinite. The second thing that we should apply here is that Vp is equal to Vn. But what is the value of Vn? Notice here that based on the current information of the circuit, it is not possible to identify the voltage at this Vn. However, because this Vb is equal to 0 volt, this implies that this Vp is also equal to 0. So Vp is 0, so hence we have Vn also equal to 0. Next, what we can do, we should apply the Kirchhoff's current law, applying the Kirchhoff's current law at node Vn, right? So if we apply the Kirchhoff's current law at this node Vn, then we have Vn minus Va divided by 25k. We can use the same analogy and the same set of rules that we have studied for the node voltage method. We can assume that all the currents are flowing out of this particular node, and hence we have a current flowing in this direction as well as the current flowing in this particular direction. So applying the Kirchhoff's current law at this particular node Va states that we have I25 plus I100 plus In, that is equal to 0. So if I say this is I25 and let us say we say this is I100, then this I25 is Vn minus this Va divided by this particular resistance, 25 kilo ohm resistance. Then we have Vn minus V naught divided by the 100 kilo ohm resistance. And because this In is also 0 because of this first constraint that we have applied, so we have In equal to 0, and that is equal to 0. And by putting down the values from this point number 2, we know that Vn is equal to 0. So putting this Vn equal to 0 and Va equal to 1 volt, we come to know that V naught is equal to minus 4 volt. Now, because this V naught is equal to minus 4 volt and it is less than, and it lies between these two biasing supply voltages, therefore we say that the transformer, that this operation amplifier is actually operating in a linear region. When actually an operation amplifier tries to go out of the linear region, for example, if we say for example, let us say that Va is equal to 4 volt. Now, going on with this particular equation, if we go on with this particular equation, then the V naught will be equal to minus 16 volt. Notice that this minus 16 volt is greater than this biasing supply voltage of minus 10 volt. So the output cannot be greater than the plus VCC and minus VCC, and hence we have, and hence the output is equal to minus 10 volt. So you see that theoretically we are getting minus 16 volt, but we cannot say that this is minus 16 volt because the biasing supply limits the output at plus minus 10 volt. So the output shall be equal to minus 10 volt, and we say that the operation amplifier is not actually operating in an amplification mode, rather it is now saturated, and it is giving a flat output voltage equal to the minus VCC. There are various important circuits that can be used in using the operation amplifier. For instance, there are two different types of amplifiers that are possible. One is an inverting amplifier and the other one is a non-inverting amplifier. So let us first start with the concept of the inverting amplifier. So inverting amplifier is the most commonly used configuration of this op amp. We have this negative, we have this positive. Positive is grounded, and we have an input signal which is applied on this negative input, which is the Vn, and then we have this resistance Rf here. Let us say this is Rs, this is Vs, and this is the V naught. This is the same circuit that we have studied just a little bit earlier. Let us do it for a generic equations and generic formula, so that we get a transfer function of how input and output voltage are related. So let me say this is Vp and this is Vn. So if I apply the Kirchhoff's current law at Vn, we get Vn minus Vs divided by Rs plus Vn minus V naught divided by Rf, and that is equal to 0. Also we have Vp is equal to Vn, that is equal to 0. So this, if we if I plug it in back in here, so that this Vn becomes equal to 0, and thereafter if I try to establish a relation between the input and the output, then V naught is equal to minus Vs into Rf over Rs, right, where this Rf over Rs is actually it decides the gain of this particular amplifier. And because of this negative sign, we have an inverting output, and hence this type of an amplifier is known as a inverting amplifier. Inverting amplifiers are very much used in almost every sort of a circuit. They are widely used in various electrical and electronic circuits, and because of their stability, they are used more often than that of a non-inverting amplifier. Notice here that if we have this gain equal to if this Rf and Rs is equal to 1, then it becomes a unity gain amplifier with an inverting output. Also we can see that one of these two resistances can be made variable, so that the output gain can also be controlled according to the needs and the requirement of a given circuit. Now let us see what is a non-inverting amplifier. Non-inverting amplifier has non-inverting amplifier has a different configuration. So let me draw the non-inverting amplifier as well. So we have, because it is a non-inverting amplifier, therefore the primary input will be applied to the input signal is applied on the positive terminal of the input, and therefore let me draw the circuit here. Let us say this is Vg, this is Rg, and here we have a ground here, and we have an output plus minus V naught here, right? So we have, this is Rf, this is Rs. Now let me first of all define the different voltages here. So this is Vn, this is Vp. Now notice here that this Vp, there is a resistance Rg which is connected between this Vp and this Vg. However, because this has an input impedance is infinite. Now because the input Rin is equal to infinity, so Ip is equal to In is equal to 0. Remember that Ip and In means the current which is entering here. This is In, and this particular I can say that this particular current is Ip. Both are equal to 0, which means that there is no drop across this Rg, right? So no voltage drop across Rg, and hence Vp is equal to Vg, and therefore that is equal to Vn, using the concept of the virtual short. Now if we apply the Kirchhoff's current law at Vn, then we have Vn over Rs plus Vn minus V naught over Rf, and that is equal to 0. So we can see here that this Vn is equal to this Vg. So if I plug in here, so that is Vg over Rs plus Vg minus V naught over Rf, that is equal to 0. So moving on with this particular thing, if I rearrange in terms of a transfer function where the input voltage is related with an output voltage, so we get V naught equals to Vg Rs plus Rf divided by Rs. And for if we want to have an amplification here, then for it must operate in a linear region. So therefore for linear region, the following condition must be true for this given operation amplifier circuit. So Rs plus Rf over Rs should be less than Vcc over Vg. If this condition is not met, then the operation amplifier will saturate and it will not operate in a linear region. Now that we have studied a few important points of operation amplifier, we are now ready and set to solve different operation amplifier circuits. Notice here that operation amplifier circuits for W211, which is an introductory course of electrical circuits, the only two important concerns are that you should always remember that the input currents Ip and In is equal to 0. So that helps a lot while applying the Kirchhoff's current law on the input side. The output current I naught is not equal to 0. It do has some finite value, but you cannot actually identify that value unless and until you have the required information on the output side. So the key of almost all the circuits of operation amplifier lies in starting from the input constraint input side and then going on to the output side. The second important point for W211 for solving the operation amplifier circuits is to remember that once we know the voltage on one of the inputs, we know the voltage on the other input. So either one is important. So we have to first calculate either the Vp or the Vn to start with the given circuit. So let us start with a very simple circuit. Let us say this is our example number 1. This is example number 1. So I will start a circuit, right? So we have this is the same circuit that we have seen earlier. So I will only be having a discussion on identifying this Vp and Vn. Here we have, for this particular circuit, we have Vp equals to 0 volt because it is directly grounded, and hence we have Vn also equal to 0 volt by virtue of the virtual short. Now let me redraw this circuit again, and this time with a different parameter. So we have, this is minus, this is plus, this is V naught. So we have this given circuit. Here we have, this is Vn and this is Vp. Again, despite the fact that we have now a voltage source connected on this positive side, because this current Ip is equal to 0, therefore the drop across this particular resistance Rg, right, the drop across Rg is Ip into Rg, that is equal to Vg, right, that is equal to Vg. So Ip into Rg is equal to Vg, and that means that this voltage drop, the Vp is equal to Vg minus Vrg. Now because this IP is equal to 0, therefore the drop across this particular resistance RG is equal to 0, and therefore the Vp is equal to Vg, and this implies that Vn is also equal to Vg, right. Let us draw another circuit and see what is the value of Vp. So now we have another circuit available here. Notice here that we have, this is negative, this is positive, so this is Vn and this is Vp. The value of Vp is not 0 in this particular case, because even if there is no current IP available here, this current source do have a loop to flow through this Rx and Ry network. So therefore the voltage Vp here is equal to Ig times the resistance, which is this Ry resistance, which is connected with the ground terminal. So for instance, if we have, if Ig is equal to 5 and this Ry is equal to 1, then we have Vp equals to 5 volt, and therefore this Vn then be equals to 5 volt. Notice that there is no way to directly calculate the value of this Vn and then moving on to this Vp. So either one of the side is very important in identifying the voltage at the input, at the inverting input or on the non-inverting input. So let us solve some circuit to identify our understanding of the operation amplifier circuits. So let me say this is example number 2. So here we have, this is our circuit. So we are tasked to find out what is the value of this I naught in this given in this operation amplifier circuit. To start with, if we notice here, this is Vp, this is Vn, and now in here we are very sure that this Vp is equal to 12 volt because it is connected directly with the voltage source. So therefore Vp is known, that is equal to 12 volt, and hence we do know what is the value of Vn by virtue of the concept of the virtual short. So Vn is also equals to 12 volt by virtual short. We can actually come up with this particular thing, that Vn is also equal to 12 volt. Now that this is equal to 12 volt, then this particular point is also equal to 12 volt, and therefore we can actually find out what is the current I flowing from this particular branch. So this current I is equal to V over R, and because this 12 volt is with respect to this particular ground terminal, so we have this 12 divided by 2k, and that is equal to 6 milliampere. Notice that this 6 milliampere current is also flowing through this 12 kilo ohm resistance, because the current IN is equal to 0. So if we apply the Kirchhoff's current law at this particular point, if we apply the Kirchhoff's current law here, then the Kirchhoff's current law states that the current entering in a node must be equal to the sum of the current that leaves the node. So there is no current which is flowing through this particular branch into this inverting input. So therefore this 6 milliampere current is actually flowing through this 12 kilo ohm resistance. So the total voltage between these 2 points V12k is equal to I into this 12k. So that is 6 milliampere into this 12 kilo ohm resistance, and that is equal to 72 volt here, right. So now we have come to know what is the total voltage across this 12 kilo ohm resistance and across this 2 kilo ohm resistance. So the total voltage V naught here is the sum of the voltage across 12 kilo ohm resistance and the voltage across this 2 kilo ohm resistance, and that is equal to 72 plus 12, that is equal to 80 84 volt. So the 84 volt is available at this output. So we have I naught equals to V over R, and that is 84 divided by this 10K, and this gives you 8.4 milliampere current. Notice that in this particular circuit, the information of the biasing voltage is not available, right? There are certain operation amplifiers available that have a biasing voltage equal to something around 100 volt as well. They are known as the power operation amplifier, normally used in some high tech industrial equipment for amplification purpose. Nevertheless, even if the output biasing voltage, if the biasing voltage is not given in a given circuit, then you have to actually solve the circuit no matter what the value is. If for instance we specify for this particular circuit what is the output voltage, then we first need to identify if it is in a linear region. If it is not in a linear region, then the output is simply equal to the biasing supply voltage, and that makes the circuit even more simplified to solve for this current I naught. So now that this 8.4 milliampere is done, we can actually now identify what is the current here. So we have a current division between these 2 points. So we have 6 milliampere current flowing in this branch and 8.4 milliampere current flowing through this 10 kilo ohm resistance. So the total output current I naught is equal to 6 milliampere plus 8.4 milliampere. This is equal to 14.4 milliampere. Notice that directly there is no way to solve for the output current. Let us do another example to further strengthen the concepts of the operation amplifier circuits. Let us say we have for this particular circuit, I naught is required. Notice here, sorry, I need to actually put in breaking. Okay. Notice here the key to solve an operation amplifier starts from the input side. So let us first identify there are two operation amplifier here. Let us say this is op amp number 1 and this is op amp number 2, and consequently we have this is VP1, this is VN1, this particular point is VN2, and this particular point is VP2. If we see clearly here that this VP2, because this current IP2 is equal to 0, all the currents into an operation amplifier are 0. So let me write them as well. So IN1 is equal to IP1 is equal to IN2 is equal to IP2, that are all equal to 0. So there is no current which flows into the given circuit, and therefore VN2 is equal to 5.8 volt. However, we have this VP1 that is equal to 5.8, and because this has a positive sign here and we have a negative sign here, so the total voltage at this particular point VP1 is equal to 7.8 volt, right? So we have now the information about the VP2, sorry, this is VP2, VN2, also we have information about VN1. So we do know what is the voltage here and what is the voltage here. Knowingly that this IN1, which is this current, as well as this particular current, they are all equal to 0. So we know that this VN1 is actually the voltage here and this VN2 is the voltage here. So now we can calculate what is the current I flowing through this 4 kilo ohm resistance. So I 4 kilo ohm is equal to Vn1 minus Vn2 divided by 4k, and that is equal to 7.8 minus 5.8 divided by 4k, and that is equal to 0.5 milliampere. Now this 0.5 milliampere is actually flowing through this 4 kilo ohm resistance, and because the current flowing through these 6 kilo ohm resistance is equal to 0, so the same amount of current is actually flowing through the 8 kilo ohm resistances. So I can therefore calculate that V8K is equal to I into 8K, and that is equal to 4 volt for both the for both the 8 kilo ohm resistance. So the net voltage here V naught is equal to V8K plus V4K plus V8K. So this is equal to 4 volt. We have 2 volt differential voltage between this 4 kilo ohm resistance is 2 volt. So 4 plus 2 plus 4, and that is equal to 10 volt is the output. So now that I have computed this V naught available here, then I naught is equal to V naught over R, and that is equal to 10 divided by 4 kilo ohm resistance, and this gives me 2.5 milliampere, and this is the answer for this particular circuit. Notice that the operation amplifier circuits are one of the most easiest concepts in linear circuit analysis course. Only you need to remember the concept of the virtual short and the concept of the input constraints. No current actually enters a given any input of an operation amplifier. The IP is equal to 0, IN is equal to 0, but we do have the output current, which is actually supplied by the biasing supply voltage plus VCC and the minus VCC. And also never try to solve a circuit. Most of the circuits are, are are actually solved wrong if you apply a Kirchhoff's current law at the output terminal of the operation amplifier. So start with the input side and then proceed to the output side to solve a given circuit. Now that up till now we have actually seen that an operation amplifier is considered an ideal operation amplifier. We assume that the input impedance is equal to infinity, and therefore there is no current which actually enters this operation amplifier. We also assume that the output resistance of an operation amplifier is equal to 0, which means that the output current is not 0, rather it has some finite value. However, there are certain constraints that are required if we want to if we want to accurately model an operation amplifier for making the output more consistent with the practical results. So let us start with the realistic model of an inverting amplifier. So with the realistic model of operation amplifier, of course the input impedance cannot be made infinite, and neither we have a practically zero output impedance. So what happen is that the realistic model of op amp. So with this realistic model op amp, we have the following circuit. So let us say we have this voltage. Let us say we have now, this is the our input, this is the Vp, here we have this Vn, and also we have in here we have this is R naught. So we have this V naught available here. Notice that with this finite value of the Ri, even if this Ri is very high, for instance, let us say that this Ri is equal to 2 mega ohm, right? This means that this current IP is not equal to 0. So is this current IN, which is not equal to 0 in this particular case. This means that the constraint that we used earlier, that Vp is equal to Vn, it is also not equal to they are not actually equal. So let me let me let me erase this thing. So Vp is not equal to Vn. So we shall actually derive the expression for the transfer characteristics of a non-inverting amplifier using this non-idealistic model or a non-ideal model of an operation amplifier. So let us draw an operation amplifier. We have an operation amplifier here. So this is Vs, this is Rs, this is Rin, and we have a feedback path as well, which is Rf. Also on the output side we have we have this R naught. This is this particular dependent source is A times Vp minus Vn, and here we have the we are trying to get the output voltage V naught. So now if you see, let us call this one node A and let us call this as node B. So let us apply the KCL at node A. So if we apply the Kirchhoff's law at node A, let me draw this as well here. So now if we apply the Kirchhoff's current law at this node A, then we have Vn, because this is Vn, this is negative input, this is the positive input, Vn minus Vs divided by Rs plus Vn minus V naught divided by Rf. Now because of the finite input impedance now, which is not in infinite here, so we do have some current with that flows into the non-inverting, into the inverting input as well as the non-inverting input. So that current is specified as plus Vn over Ri, and that is equal to 0. Let us say this is equation number 1. Now also if I apply the Kirchhoff's current law at node B, which is this at our output, then that is equal to V naught minus Vn divided by Rf plus V naught minus A times Vp minus Vn divided by R naught, and that is equal to 0. So we have two equations available here. Now if I rearrange these two equations, we get 1 over Rs plus 1 over Ri plus 1 over Rf times Vn minus 1 over Rf V naught, that is equal to 1 over Rs into Vs. Let us say this is equation number 3, and also we have A over R naught minus 1 over Rf into V of n plus 1 over Rf plus 1 over R naught to V naught is equal to 0, and this is equation number 4. Now we have started from this particular practical circuit or a realistic model of an operation amplifier, where we have actually assumed that the output impedance is not 0 now. We do have some finite output impedance R naught, and we also assume that there is a finite, there is no longer we have an infinite input impedance. So we do have some current which is flowing into this particular terminal, and hence we cannot say that Vp is equal to Vn. So we started with the application of the Kirchhoff's current law at this particular node A as well as on this particular node B. So we have actually applied the Kirchhoff's current law, and then after we rearrange the equation number 1 and 2 in terms of the variable V and V naught and Vs. So we have equation number, we have got come up with the equation number 3 and 4. Now if we apply, if we use the operation, if we apply the matrix operation using matrix, 3 and 4 can be rearranged as V naught is equal to Vs minus A plus R naught over Rf, and that is equal to Rs Rf into 1 plus A plus R naught over Ri plus Rs over Ri plus 1 plus R naught over Rf, and this gives us the, and this gives equation number 5 gives us the exact relation between input and output if we do not consider ideal characteristics of an operation amplifier. Notice here that for an ideal operation amplifier, the values of R in is equal to infinity, R naught is equal to 0, and if we use the ideal characteristics of an operation amplifier, then V naught is equal to Rf over Rs into V of S, and this is exactly the same that we have actually obtained for the circuits where we have where we have a non-inverting where we studied the inverting amplifier with the ideal characteristics. So you see that non-idealities in electrical circuit can also be analyzed using the concept that we have built so far. But right now, most of the time, it is important to see the actual difference in the output if the ideal model of an operation amplifier is not adopted here. So that's all for the concept of the operation amplifier. I hope you all like the lecture series on W211. I advise all of you, all the listeners, to actually solve the circuits of linear circuit analysis, chapter number 5, to have a basic, to have a firm grip on the operation amplifier. There are some very interesting circuits about operation amplifier given in the textbooks written by Richard C. Dorff and Nilsson, and also by the David J. Irwin. So try to solve them, and that will help you in grasping the basic concepts of operation amplifier very well. Till there, take care. Thank you very much.